Okay, welcome everybody, and welcome to the first public lecture in this year's series of Our Changing World. I'd particularly like to welcome all our new undergraduate students and our postgraduate students, and of course the wider general public to hear about the topic tonight. The lecture series itself is designed really to stimulate debate in a highly topical area, especially in terms of global challenges facing society, and really how academia is trying to address those challenges. And today's talk, which is regarding the application and uses of robots, is actually no exception as being very, very highly topical. If any of you were looking at Sky News, for example, a couple of weeks ago, actually Sky News were recording from tonight's speaker's lab on the hour, every hour, for a whole day. And there's also been a lot of news in BBC and other media outlets. So today's speaker is Professor Sethu Vijayakumar, who is the Professor of Robotics, the Director of the Edinburgh Centre for Robotics, and he holds a Microsoft Research Royal Society of Engineering chair in robotics here in the School of Informatics in Edinburgh. Now, Sethu has really pioneered the use of large-scale machine learning techniques in the real-time control of large degree of freedom anthropomorphic robotic systems. What do I mean by that? Actually, many of you will probably be familiar with, for example, the Honda Asimo robot that many of you will have seen sort of dancing on the TV and so on. It's that sort of anthropomorphic robot. It's one of the many things that he does. His research interests are very broad. They range from machine learning through to human motor control and computational neuroscience that he integrates into a lot of his work. And, of course, he's published very widely, and his work has been widely recognized by many awards, including the IAE Vincent Bendix Award, the Japanese Monbusho Fellowship, and he's also a Fellow of the Royal Society of Edinburgh. So in today's lecture, he will look at technological advances in robotics that have transformed really our daily lives, and really start a discussion about the trade-off between autonomy and control that we may be willing to admit to repeat the maximal benefits of these approaches. So his talk tonight is called Sharing Autonomy and Responsibility. The robots are ready, are you? Sethu.
Thank you all for giving up your evening and coming to listen to this talk. I'm hoping that we are here to have an interactive debate about an interesting topic. So what I plan to do in the next 45 minutes or so is to give you a glimpse of the scientific advances that we've been making in the area of robotics, and then literally open the floor to some of the more controversial issues in terms of the use of robots in today's society. So why have I focused on this topic of sharing autonomy? It's because traditionally robots have always looked at a scenario where you teleoperate them in the sense of you either manually program them to do a particular thing, or you actually make a movement with your hand or your limbs and the robot literally mimics that. So you can think about scenarios in sort of remote handling where they've done teleoperation. So the robots of today are moving away from such kind of teleoperated or pre-programmed things that sit inside factories and cages to scenarios where you're looking for more significant autonomy. So what do I mean by autonomy is robots which can make decisions for itself, robots which can plan on itself. You're given some high-level goals, like in this case, opening a door. This humanoid robot is designed to actually make crucial decisions for itself. Things like avoiding an obstacle or even maintaining a balance while it's moving. So that's the big aim. That's where the research is leading us to. But what I feel in the next 5 to 10 years, we're going to, the kind of things that are going to actually come into the society where you and me live, it's something in between, is what I call shared autonomy. And what do I mean by shared autonomy? It's a concept where the humans are still in the loop. Most of the volition of the actual task comes from the human, but the robots are helping you execute it much more efficiently, much more robustly, and cutting out lots of human error. At least that's the vision. So, whether you agree or not is a different matter. So, on that sort of stream of thoughts, so robots are indeed becoming ubiquitous in today's world. You've seen robots being applied already in domains ranging from prosthetics and exoskeletons to self-driving cars. There's a big initiative in the UK for UK-bred autonomous cars, underwater robots, medical robots, service robots, and in areas ranging from self-driving cars and trucks on the highway to things like exoskeletons for the aged, for augmenting people's capabilities, to things like collaborative manufacturing and nuclear decommissioning, which is actually a big problem at the moment. So there are robots that are in various levels of deployment in these domains. But it turns out that in spite of all this nice list of places where robots are useful, there are still lots of open challenges. And the open challenges come from the fact that robots of today are not independent things or entities that just do what it's supposed to do. It's actually interacting with you and me, it's interacting with the environment, it's interacting with other robots. And that creates a lot of problems, like you've got multiple contacts, you've got nonlinearities. So those of you who are coming from the engineering background will understand most of these sort of terms, which is highly constrained environment, noisy sensing apparatus, and all of these you have to make sure that it operates under significant autonomy while being safe. And that's the key word, it's while being safe. Otherwise, you and me, we're not going to trust robots to do lots of the things that we care about. So I think what I'm going to try and do in the first half of my lecture is to tell you a little bit about the technologies that we've been developing to help alleviate some of these problems, making sure we get much more robust behavior, much more repeatable behavior, and in the second half, try to be slightly more open in terms of the actual social issues, the ethics underlying the use of these robots. So if I break my talk down, the roadmap, indeed you can think about these issues as two key domains. One, the technological challenges and solutions, and indeed the societal impact and implications of the use of these robots in today's society. And under these things, there are a few keywords that you can actually look at. You can look at things like robustness, adaptability, and safety, and most of these keywords have to deal with technological advances that can literally solve these problems. Okay. On the other hand, if you look at the main area of today's talk in terms of what level of autonomy are you willing to allow the robots, that combined with things like security, how can you make sure a technologically superior robot is secure enough that's in such a way that somebody can't hack into your system and make it do things that you don't want it to do. So that is somehow bridging the gap between technological sort of challenges and the societal impacts. So this is somewhere, it's a gray area in between those two things. Whereas something like ethics, jobs, are the robots going to take your jobs? This was the big news in BBC a couple of weeks ago. So those are more, I would say, something which has to deal with the society, how we use the robots, and how and where we like them to sit in the whole fabric of today's society. Okay, so I'm going to start with the first bit. Okay, so robustness, adaptability, and safety. So what are interesting scientific advancements that we've been making, that the community has been making to enable this. So the first thing, obviously, is for any robot or any artificial intelligence system to work, you need it to make sense of the world around you. And for that, you need something called tracking. So you need to be able to robustly track the world around you. And here's a little video that shows some research that's coming out of our lab, which is essentially trying to track the hand of the robot, the mug or the object of interest, and, for example, this highly occluded bottle of drink. So the challenges underlying this tracking are that you get lots of occlusion. Sometimes it's outside the depth camera range. And in a moment, you will see that the camera itself, while it's stationary at the moment, needs to move. For example, if you deploy a camera on a robot, it's sort of, you shouldn't think of it as something that is static. So the robot moves, the camera moves with it. So you need to be able to do this kind of robust tracking while there is camera motion. So you can see this example of servoing. It's called visual servoing. In other words, trying to track where the mug is and making sure the end of the bottle is above the mug, but doing that while there's camera motion, significant jitter and occlusion. And that is a significant sort of challenge in computer vision. So this is one of the solutions that's come out of our lab. There are many, many groups in the world working on robust solutions to doing tracking. You and me take that for granted in trying to follow an object around the world, but it's quite hard to get a robot to do it. Okay, so that was purely tracking. But just naive tracking is not enough, because you need to integrate that tracking, the computer vision element and the tracking, with really making sense of the world around you, which means making sense of the entire environment around you. So what does that literally mean? It means you have some complicated suite of sensors, like LiDARs, some depth and stereo cameras, and maybe other things like touch sensors. And it has to take that kind of complex set of sensors and then build a map of the world around you. So on your way up to this lecture hall, many of you probably come to this lecture hall for the first time, but you were very good at not tripping over and finding your way up and finding a seat. It's not trivial for a robot to do. So what we've been working on is we've been looking at sensor technologies which can do this very robustly, but also integrating that with some control, with some robust control, especially on rather complicated humanoid platforms. An example of that is a collaboration we have with the NASA, JSC, Johnson Space Center, and we are getting a copy of the Valkyrie humanoid robot, which is co-developed with NASA in December or January of early next year. So those of you who are interested in looking at this platform, please come and find us. It'll be in one of the rooms in the informatics forum. So the kind of things that we've been doing are, so this is a collaboration with MIT on the DARPA Robotics Challenge, and this is a humanoid robot. It's a 1.6 meter tall robot, about 150, 160 kilograms. But the idea is we are able to now, in real time, use the sensors on board to create a local view of the world around you. And this is the camera view of the robot, and do things like find out some depth information, plan some steps, and make sure the execution of this step happens in such a way that the robot doesn't fall over. It's very easy for the robot to fall over. Believe me, if you've seen some of the outtakes of the DRC challenge, many of you would have seen that it's easier for the robot to fall over than not. So this is literally getting sensing and control in the loop, and the steps involved in doing that are straightforward to break it down. So one is you need to make sense of the sort of terrain, so depth information, so you can take your LiDAR and camera information and do some sort of terrain segmentation. And then you can use your favorite machine learning algorithm to cluster this into some appropriate depth information and from that, you can figure out the stability constraints on the robot. This is something we call the ZMP constraint, or the foot polygon, support polygon. And then once you have that, then you have to execute it in the presence of sensory noise. So these are all the steps that are involved in getting a complicated robot to walk on a rather unstructured terrain, for example. Okay, so that was getting the sensing part. Not sure people at the back can see this, but this is a little comic strip that is courtesy of Daniel Sidobre from LAS in France. I'll put up the whole thing. If you can read it, you should read it. But essentially, this is a little cartoon which shows the current bridge between the robotic control scenarios and human intuitive scenarios that people actually reason in. So this is a little thing which says here, overlords of tomorrow taking over and saying, do you want something? And this says yes, and then he gives an instruction to the human to bring a drink which is sort of specified in coordinates which are much more intuitive to robots. And then the human comes back and says, sorry, can't do it. And then the interesting thing is robot-human interaction rather than human-robot interaction. So the whole point here is there's a little gap between what is useful as a human sort of intuitive way of thinking and what robots need as a way of actually executing those movements. So to be able to do that, we've been looking at some work on representation. So you can represent the world as something like, for example, if I'm going to lift something here, I would say something is kept on the table. On the other hand, robots need something more precise. You have to say positions X, Y, and Z. So how do you bridge those two gaps? How do you bridge the representation between those two things? And there's some research that we've been working on in terms of using novel ways of representing both positions of robots, the environment around you, and the motion. I won't go into the details. There's some things called interaction mesh, harmonic fields, relational tangent planes. But these are all, you can think of them as intuitive ways of representing the relationship between objects and robots. But I'll show you a little video which actually illustrates the point. So here's a robot arm trying to reach inside this box. And typically, you would have given it a position X, Y, and Z to reach. But if we use topological coordinates which are based on relationship between objects and the space, then the space of what is inside and outside moves with the movement of the box. And if that happens, then you can replan, you can retarget the motion very intuitively. So you can see here, unless it's going to hit the edge of the box, the robot's not going to change its plans. So this is the way of intuitively actually showing that you can actually, when I say reach inside a box, I do not mean actually X, Y, Z inside the center of the box, but I actually mean as long as you're inside the box, it's okay. And this is the way of bridging those two things. And where does this kind of planning or representation become useful? They become useful when we are using very complex robots in rather complex environments. So for example, this is a collaboration with something called OC Robotics. So I'm going to just mute this. But this is an example of a snake robot that is being used in an environment that is, you'll see in a moment, rather complicated, harsh, typically in nuclear decommissioning tasks. And the planning that needs to happen for these robots, the traditional ways of doing classical sort of planning algorithms don't work if you don't use the right kind of representation. Purely because it's complex, you need fast reactive motion, you don't have the whole day to react to some things. And this is an example of a robot going into, say, a rather complicated environment, in this case doing a little weld, and even sort of going into nooks and crannies and doing, in this case, quite a intricate job of surveying what's inside there. So hazardous environments where you and me don't want to actually go. So to get planning in this kind of multi-degree of freedom robotic platforms using classical techniques is quite hard, and that's where we are trying to push the planning technologies, the representation that we just talked about, in rather interesting domains. And it can be everything from inspection robots to things where you've got, and this gets applied, the same technology gets applied to inside your body. So if you want to have a surgery inside a body and you want to do it in an as non-invasive fashion as possible, because that reduces your recovery time. So the same technologies, different scale, but same technologies work. Okay, so another bit of innovation that we've been looking at. So in spite of having very specific or good sensors and having the right representation, invariably you will still have errors in your system. So you need to build robotic platforms which are inherently safe. So for you and me, for very, in simple terms, you need systems that are able to deal with things going wrong. And one way of doing that is by having what we call flexible joints. So robots which have got motors and they're not rigidly connected to an end effector, but they are connected through a very stiff spring so that they're passively compliant. So this is a concept called compliant control. So basically you put springs in between joints and make them passively compliant, make them passively less threatening in case something goes wrong. So mechanically, that's a beautiful principle. There are lots of work in that area. What makes it hard is controlling them precisely is actually very, very hard. So the moment you put springs in it, it becomes hard to sort of control them very precisely. And again, there's a whole range of research that goes into making this work efficiently. So just to give you a little sort of insight into why do we need compliant control. So we've got these exoskeletons. So these are things where, for example, people wear them for example, if you've lost a limb, or if you've had a stroke, or if you are weak in certain parts of your limbs. So the technology is now coming to a stage where we can build robotic platforms or exoskeletons which you can wear and help you augment your capabilities. So when you have such technology attached to your body, it better be safe. You don't want things, it's having its own mind of its own, right? So here's a little video of applying a compliant control-based planning schemes to, in this case, a bimanual robot. It's meant to be a manufacturing robot. But you can see the flexibility. So this is a research prototype. So you can see when a person is in the loop and tries to do something, the robot nicely gives way and ensures that it's still making sure that the task is being fulfilled while the robot still gives way and doesn't, in this case, react with a movement that is dangerous or problematic. So that's an example of one way of dealing with people in the loop and making sure it's safe. Okay, so a quick slide to flash for the machine learning and the computer scientists in the crowd. Of course, hardware, sensing, and representation is not good enough. You need to plan. To be able to plan, you need to be able to write some logic. You need to be able to do some inference over state transformations. And this is a little schematic which shows you that there's a step in between, going from sensing to actions, which involves some maths behind it. And this is the Bayesian inference slide that I usually put up. I'm not, again, going to go into the details, but those of you who understand it, you know what it means. But as a consequence of that, you can get things like this biped to walk. So you can get a robot. So this is a prototype robot. It's a first of its kind in the world, which is able to change its damping and stiffness at every joint. And this is, again, coming from some very talented PhD students right across the street in informatics. This is a PhD thesis of one of the students, and what's unique about it is the aim is to get robots which can adapt to terrain and environment. For example, if you and me, we walk on a very stiff piece of ground, then we have a particular level of stiffness on our legs. But the moment you walk on grass or something much more spongy, then you change your stiffness while walking. And that's the whole idea, is you're able to adapt and change according to things. Okay, last one of the technological innovations. We are very good at adapting our behavior when some things change. So a typical control loop for a robot to be controlled would look like you have some sort of task that you want to do, you have some goodness criterion, and you get a robot, and you have a planner which generates some sort of commands to send to the robot, and then you go around in a loop, in a control loop. The problem with that is if something changes. For example, the robot lifts something quite heavy, or I put a little strap on its leg, or some dynamics change during the operation, then you have to go back to your sort of Newtonian dynamics and your paper and pen and redo the actual control algorithm. But it turns out that by using machine learning, you're using data, you're able to learn from experience, and it's not easy to do it, but you can, using the right tools, you can make sure this happens fast enough and robustly enough to be able to adapt to changing situations. And that's what we try to do, and that's the other missing bit in terms of getting robots to adapt and be just like you and me. So an example of that, and this is work from a long time ago, this is part of my PhD work, so I'd still like to show this video. So here's an example of a robot hand moving its arms to reach for this red ball, and just like a baby does, it's trying out different forces. It's what we call a high gain PD control. So it's very stiff, it's not at all compliant, so it doesn't give in. But it's learning the relationship between the forces that the robot applies at every joint and the end effector movement. So all the time it's figuring out the relationship between the actions it's taking and the consequence. And it's storing it away in a clever way. Storing it away using some clever representation, using machine learning techniques from functional approximation to do this. So once it does that, then you can get the robot to do something more fancy. In other words, learn tool use. So it can explore the world of actions, in this case, the movement of the fingertip in the XY plane, and look at what happens to the pole. Essentially, it's looking at the camera image, the red and the XYZ of the red and the XYZ of the yellow, and figuring out whether it's horizontal or not. And eventually, it figures out that for a particular state space, a particular set of actions will result in the pole being upright. And this is an example of not programming a robot to do everything, but rather using data to learn and essentially do the task that you care about. And this is quite crucial because it's very hard for you and me to understand and program for every eventuality in the world. If you had this stick which is slightly heavier or slightly shorter or slightly longer, you need completely different dynamics. And the whole point is, from data, you're able to learn these things efficiently and adapt. It doesn't mean that you throw away all the nice control theory and the Newtonian dynamics, because learning everything completely from scratch will take forever. Genetics and evolution has happened for a reason. So I think, but you can combine them with training to make it work. Okay, so that was the bit about what are the technological challenges and some of the solutions that we can consider to make sure that the robots are much more robust. Technologically, we can push the envelope and make them work. So the next bits, especially what level of autonomy do people or are people willing to share? And concerns about security are interesting questions in itself, and that's what I want to get to next. So when we think about sharing autonomy, okay, so already there are lots of new research and solutions that are coming out into the market. So Toyota recently had an announcement about a new program. They wanted to make robots or autonomous driving cars which would be collision-free, no accidents. So 0 accidents is the strapline. Another robot is a bedside robot. So by the way, this is not just the arm. It includes a robot bed. So it'll basically, it's a bed with an arm helping you sort of, in this case, if you have a stroke or if you're infirm, it'll help you feed in as independent a fashion as possible. And of course, probably most of you here are aware of the Google self-driving cars. And of course, so this concept of sharing autonomy, in other words, volition coming from humans, but the actual task being done by the robots, that extends to beyond these things. Now we've got exoskeletons, rehabilitation robots. The DARPA Robotics Challenge is something that just had a big impact over the last year. So I'll tell you what it means by that. So the DARPA Robotics Challenge was a big challenge that was run. Basically, it was coming out of, the inspiration was out of getting robots to work in disaster recovery scenarios like in the Fukushima, the nuclear power plant disaster following the earthquake and the tsunami. And the whole idea was to have large robots like this actually have a bunch of tasks like this: to drive a car, dismount, open a door, operate a valve, cut through some wall. In this case, it was a hardboard wall. It wasn't brick. Do a surprise task like switch on a switch or a hose, and finally walk through rubble and climb a stair. So this was the whole setup. It was a challenge for getting robots to do this fairly autonomously. Okay, so many robots succeeded, but the reality of the control underlying that was something like this. So the robots were on the field, but there was a whole back suit of people doing this thing with large screens, doing some user input in terms of saying, is this okay to go, verifying things. So this is exactly the concept of human-in-the-loop shared autonomy, where robots are doing many things autonomously, like balancing itself so that it doesn't fall over, or doing things like moving its arms, solving the kinematics autonomously. But there's still significant human-in-the-loop in terms of saying what is it that you need to grab, what is the action you need to do. So a lot of things were still human-in-the-loop kind of solutions. So the aim is to move towards safer, much more fully autonomous systems, but the reality is this slider that I talked to you about early on. People are still unclear where should that slider actually be. So what I want to do is to actually give you a live demo of a concept which will tell you or get across the concept of shared autonomy in a much more sort of organic fashion. So for that, I'm going to need a volunteer, but what we're going to use this prosthetic hand, which is actually a collaboration with a company called Touch Bionics, based in Livingston, and this is a prosthetic hand that's worn by patients who've lost a limb. And the technology underlying the control of that is pretty straightforward. So that's a little video which shows you the EMG sensors. So there are some EMG sensors which sense the muscle activation of your hands, and then you can use a nice decoding algorithm to control or find out what is the action that the person is making and literally mimic that action. So in this case, it is 100% mimicking of the action, right? It's 100% teleoperation because literally the EMG sensor decodes the actions in the joint angles of the person's movement, the force, and mimics that on the robot hand. But this is slightly different. So here, the volition of the movement comes from the person who's wearing it, but a lot of the smarts are actually embedded in the hand. So can I get a volunteer to come in? Okay, you want to come up? Okay, so what I'm going to do is to get him to, what's your name?
Ankit.
Ankit, okay. I'm going to get you to, you want to come around? I'm going to get you to wear this hand, and it's heavier than you think, so you may want to brace yourself. Okay. Is that the right thing to do? Okay. Okay. Okay, good. So, and then what I'm going to do is to wear, so by the way, these are EMG sensors. These are sensors which sense the muscle activity on my hand. Okay, so okay, now let's see. So I'm going to turn it on, and you can see that when I make a particular motion with my wrist, the hand literally mimics that. And we can do something even cleverer. If you want to come along with me, we're now tied for life. Okay, so let's go back there. Okay, so what we're going to try and do is to try and grasp this bottle of water. And you want to turn it around so it's a bit, and you can see that it can sort of lift a bottle full of water and release it, and also it can grab rather more complicated objects like a ball. So what is the shared autonomy element here? So if you want to hang on to this ball and place it here while I look away. So the point is that while I'm looking away, I don't need to look at the object that I'm controlling to actually finish grasping that. And I'm going to release it now. So literally, the volition of opening and closing is coming from my hand, but the precise point at which the hand should stop moving its fingers is the smarts are built into the hand. So you can see that the volition is coming from the person, but a lot of the smarts, the autonomy, significant autonomy, is already in the hand. So maybe what we can do is we can show you I'll try one more thing. So can I get one more volunteer? Can I have a female volunteer, if that's from a gender? Come in. Okay. So now we're going to try something that's more risky. Okay. No electric shocks involved. No electric shocks involved. But what we're going to try and do is to see if the electronics that we've just the decoding algorithm, the electronics that we've built in, does it generalize across people? In other words, instead of it decoding my sort of muscle signals, whether you can, what's your name? Ines. Ines. Okay, whether we can decode your muscle signals. Okay, so it may or may not work. So I may want to. Okay, let's try that. Okay, so what I want you to do is to just move your wrist left and right. Yeah. Very good. All the way the other direction. Okay, try again. Okay, it's just the polarity is reversed, but that's okay. But she's able to. So now we can get her to. Okay, try again. No. Okay, you got to try harder. Other way. Yeah. Okay, let me do one thing. Let me try and turn it around so that maybe that might make it easier. But okay, let's try again. Okay, better. Okay. Okay. Well done. Okay, thank you. Thank you. Yeah, sure. Thank you. So you now saw that that's a real example of human-in-the-loop autonomy, shared autonomy. And this, as I said, this is a partnership with a local company called Touch Bionics. And this is an example of where research goes into products, something quite useful. So, but having said that, this nicely tags on to the other interesting keyword of today, which is security. So imagine wearing a device like that and walking around, and there's a little hacker who's literally able to gain access to some of the control algorithms. So, and this is not fiction. In April 25th this year, there was a little prototype demo from the University of Washington. Said they had a little prototype medical robot device which somebody could hack into and control the operation of some of these things. Examples of hacked autonomous cars, car control system and sensing system has been around since 2013. It's been mostly proof of concept, again, research, but it highlights the fact that you need significant research investment in research which not only builds robots but also looks at how to make it secure. Just like your internet communications, there are lots of work in terms of looking at how to make your communication secure. You do mobile banking these days, but we are able to make it secure, hopefully. But same story. So the robots are the arms and legs of the Internet of Things, and the idea is how do you make some of these things very secure. There was a news quite recently, the self-driving cars hacked using laser pointer. So not quite hacked, what it did was it just confused the LiDAR sensor by shining a powerful laser. But indeed, so these are ways in which you can get disrupted. There are things that you need to worry about. So the real implication of that, the food for thought, is when something goes wrong, who is responsible? Okay, that's the question that I don't have an answer to that. So this is something that we should potentially, think about. For example, from a purely logistics point of view, how do we deal with insurance claims following an accident in an autonomous driving car? The flip side of that is, so Uber hired the guy who hacked the Jeep Cherokee to develop safer driverless cars. So basically, if you are good at doing that, you might end up getting a multi-million-dollar job. But that has been, it's nothing new. That has been the scenario with McAfee and the viruses and all this. So this isn't something new. But we do need to think about these issues and securities when we talk about robotics now, because robots of today are much more connected, much more integrated, and they are going to be much more linked into the fabric of today's society. Okay. So, the other bit I want to talk about is a bit of ethics and jobs. So, I'm not a qualified person to talk about this in any detail. So, this is more some thoughts that have come to my mind, also inspired by some very good people in the domain, in the field. But certainly, this is more meant to be a reflection on things that we need to care about, we need to worry about. Okay? So some of the next slides are adapted from a wonderful lecture I heard from Professor Benjamin Cupers from the University of Michigan in the informatics forum a few months ago. And so he had a much more detailed view of these things. But I'm just going to take up one particular snippet from that talk and look at, so if you think about what is the definition of morality and ethics, it's basically, you can sort of look up a dictionary, principles concerning the distinction between right and wrong, a good and bad behavior, so ethics, rights and wrongs. Okay? It's a particular system of values and principles, especially held by a society or a particular person, and it sort of quantifies the extent to which an action is right or wrong. Okay, it's pretty straightforward. But now the question we can ask is, must a self-driving car make a moral decision? Or are there going to be scenarios where a self-driving car would have to make a moral decision? Okay, let me put you in the hot seat. Okay, so a car is driving down a narrow street with parked cars all around. Suddenly, an unseen pedestrian steps in front of the car. So, what should the car do? Okay, obviously, if it got enough time to brake, that's the right thing to do. What if not? Okay, let me slightly complicate this. So a autonomous driving car like this, not necessarily the Google car. So, a friendly-looking car. But let me slightly complicate the situation by giving you some more details. Okay, the car has 5 passengers. The pedestrian who stepped in front of it is a young child, and veering to the right to miss the child will hit the wall, possibly injuring or killing the passenger. So what should the car do? So I'm sure all of you have got different thoughts about it, and there's an interesting debate about all of these scenarios. But before you jump to any conclusion, I want to put out another little interesting piece of an artificial problem, and it's called the utilitarian problem. It is to do with the utility of one's actions. How good is your action for yourself, for your immediate peers, and for your society? So there's a whole formalism underlying that. In reinforcement learning, those of you who are computer scientists would say, oh, we just write down the value function and we get it. But there are lots of interesting debates around this. So let's look at that. Okay, let's look at an artificial utilitarian problem. The trolley problem. Again, this is inspired directly from Ben's talk. So that's the problem. Okay, so you have the switch. The trolley is coming down at breakneck speed. Switching the trolley saves 5 but kills 1. So most people apparently would throw the switch to save the 5 people. Why? Because it looks like a utilitarian decision. Okay, and many of you would have different answers to that. Okay, now let me slightly complicate this. The footbridge problem. So we create another trolley with the same utilitarian calculation, but now you push a person, politically probably not correct to call him a fat person, but saves 5. Most people probably would not push the fat man. Why is it okay to let 5 people die in this case? The utilitarian calculation does not prevail in this case. Okay, so this is an interesting debate. Okay, let's go even further, do something really nasty, straight from the fiction books. Okay, the transplant problem. So a healthy middle-aged man is sedated and waiting for a routine colonoscopy, and you've got 5 biocompatible person who will die without organ transplants. So, do you, the surgeon, sacrifice the 1 to save the 5? I think society clearly tells there's an answer to that in today's society. Okay? So, but the point is, forget the sensing, forget the uncertainty in the actuation. Assuming you've got perfect robots doing perfect sensing, perfect sense of the world around you, still there are important decisions which even you and me have a hard time making a real, a proper 100% guaranteed decision about, depending on the society you live in, depending upon your peers, depending upon other things. So, for example, if you ask people, apparently, I haven't done this myself, this experiment, but some of the emotional responses to this 3 problems are things like, people are going to die, I got to help. So it's a lot better if I switch. So too bad about the one guy. Okay. So the footbridge problem, people are going to die, got to help, but I just can't kill the fat man. Okay? The transplant problem, I just can't kill my patient, he depends on me, so too bad about these other 5 people. So apparently these are the responses. But where does this, what is this underlying message from this kind of response of the people? Perhaps the underlying response is there are different scales at which we make this judgment of morality, and some things are easy to quantify and codify and make it into rules. Others are, there's lots of gray areas otherwise. For example, if you apply a response rule to the scenario, if the choice is unambiguous, then it's fine. Then you make the switch. Otherwise, you have to make a consequential deliberation of this task, and then you basically take the lesser of the 2 evils, perhaps. But there are other people who would say, this one person's life is not in my hands, so I should not make that active decision, for example. There's another interesting thing, which is slower search for appropriate framework. But the big point I want you to take across from here is this: the value of trust in predictable behavior. So people put a huge onus on being predictable, and robots are exactly the same. So if you get robots which are predictable, that's a good thing. So being predictable there's a high value in today's society on being predictable. Whether it's good or bad is a whole different thing, but there's a food for thought to think about. Okay, so the last bit I want to get across before I open the floor is about jobs. Okay, so we've looked at technology, we've looked at the sort of security, we've looked at the problems that can happen and the moral dilemmas sometimes people face with robots. But, as was mentioned earlier, Sky News was live and BBC was talking about AI and impact, about lives and jobs all of last week. There was all these things about, people are going to lose jobs. One view is that retraining people for more comfortable jobs gives them more leisure, more family time. I want to stop by pointing you to prospective researchers, students who want to play with some of these robots. We've got a wonderful facility down here called Edinburgh Centre for Robotics with some of the latest and the coolest gadgets. And if you are thinking of doing a research in this domain, either a PhD or a master's degree, please come and contact us, get in touch with us, because lots of exciting opportunities. Again, I want to open the floor for questions, but I want to show you 2 videos and challenge any of you here, including the roboticists in the crowd, to try and mimic these 2 amazing individuals or people.
You guys want to maybe get out of your way, all right. Don't be nervous. No problem. Make sure you don't lose me. Get tall, lads.
I want to stop with this. Obstacle avoidance, sensing, prediction, and dexterity, all in one. Thank you, and I'm happy to answer any questions.
I was just going to ask you if you could tell us a little bit more about the commercialization of some of these projects, and particularly, I suppose, whether some of the ethical questions might become more obvious once some of these products have actually gone to market. And I just know, Microsoft is funding some of this work, and whether there's some risks associated with how these actually get to consumers eventually, particularly with Microsoft being in the lead at the moment.
We do a lot of research in our labs, and when we do this research, we look at fundamental problems, but we also have some sort of technology, some solutions, some problems, first of all, some problems in mind, and then some technological solutions to it. But now, when it finally reaches the consumer, the form it takes has evolved 3 or 4 steps. So there is this thing called the TRL levels, or technology readiness levels. And so the high technology readiness levels are when the products are really ready to go to market. The low ones are when it's at research level. And at low TRL levels, then we look at the core technology and worry less about the ethics. And as it progresses, and if we think this is viable solutions to some of the problems, then we seriously start to look into whether some of the questions here, whether this is something that is worth putting out into the market, whether it creates a conflict of interest, whether it creates issues. So specifically, guys like Toyota, Honda, KUKA robots, so they've been looking at some of the technologies which some of them are no-brainers. So for example, the healthcare ones, in which the sort of helping the elderly with the mobility kind of stuff, there I think it's a no-brainer, because otherwise they would have been highly dependent. They would not have been able to come back to their homes. They would have been in hospitals, in care homes. So there are some easy ones. So there are others which are more complicated, which are to do with augmenting human sort of capabilities, whether you use exoskeletons to change the way we are. And that's a whole set of ethical issues, and it's been explored significantly in the stem cells research domain, and very similar things will eventually come to bear upon robotics when we get more in sort of invasive things and others. But I think it's very, very sort of domain specific, and there is no real little magic sort of formula which can turn a research prototype into a product in an ethical fashion, because the questions that come up are very, very different.
I was just wondering about some of the economic implications. For example, with your self-driving car, what if you had somebody who was fabulously wealthy and had one of these cars, and no matter what hard coding the manufacturers had imposed on it, decided, I'm going to hire a hacker, he's going to fix my car, that under no circumstances is it to jeopardize my family over anybody else. It will drive straight over that child. And just in general, if you're very wealthy, you can buy all these things. If you're not particularly wealthy, then no exoskeleton for you, that kind of thing.
Very good question. And I think I'd rather open the floor open the question to the audience. But my preliminary thoughts are that one way of preventing something like that is by making sure there is certain parts of the system that are off limits for people to tamper with. The moment you open a little screw, it shuts down, and then it has to go back to the factory. But again, that's not a foolproof answer, because there are ways, I'm sure people would figure out ways of doing things otherwise. So the only sort of the one way of focusing that effort is to standardize some of these things and make it so if you've got standardized products, and it has to do with predictability as well. So the moment you start tampering with some device, then the predictability goes away, and then when there are other cars driving, or a human, there may be sort of mixed human drivers and autonomous drivers, then it's very hard for the human to predict what the autonomous car is going to do. So there's a whole bunch of issues there, and I don't have an answer to your question of what level should we put the sort of tamper-proofness, so to say. So because one way of doing it is making sure that the moment somebody tampers with some critical element of this, then it shuts down and it's useless. The device is useless.
Could I come back to you about the no-brainer
Sure.
for medical devices?
Okay.
We've had simple medical robots for decades, if not half a century. Pulmonary ventilation, renal support, lots of different machinery, and it spawns more ethical problems than we ever believed possible. In do you continue with these sort of support systems? Who gets these systems? When you talk about supporting old people, you only got to read Atul Gawande's book about aging to realize that a lot of people say, I've lived too long. You don't need to support those people any longer. You need to just help them in the lives that they have rather than put them onto extra bits of machinery.
I agree. I totally agree. And again, I think I'm not in a position to comment in any depth on that, but I think this whole issue of life support versus augmenting people's or sort of, making their lives better. So when I said no-brainer, I was referring to the fact that if it improves the quality of life of a person from being, say, a paraplegic or a disabled person to making them independent, then I think that is possibly the right thing to do. But certainly in terms of the life support system, in terms of the whole issue of palliative care, it's an open area. So I don't think roboticists are the most sensitive people to actually debate about that. But I think it's a very important issue. Thank you.
How do you feel that as robots take over more jobs and become more autonomous, that will affect the job market? So, for example, in your talk, we saw that there was shared autonomy allowing people to be retrained to do the more skilled but more comfortable job. Mm-hmm. What happens when we have fully autonomous robots that can do almost any job? Where do you see sort of people earning a living, and or whether we will even remain in a system which relies on people having to earn a living?
Right. So I think this was the whole topic of the BBC coverage last 2 weeks ago, and there was even a little app they had about how replaceable is your job, and you put in your details and says, you are highly unlikely to be replaced by a robot, and there was another bit that says, start looking for a new CV. So I think there's a lot of speculation about that, and I think I'm not the kind of person who would like to make predictions and sort of things, 10 years down the line, 5 years down the line. It's very hard to predict. But I think there were similar concerns at the beginning of the industrial age in terms of saying, there used to be weavers who were creating cloth, and then there was this steam engines took over big textile, large-scale manufacturing. What are they going to do? Many such jobs, so agricultural jobs. So we have gone through phases in history about automation taking over some of the jobs and people finding other things to do, or indeed creating new jobs, new pastimes, new jobs, new ways of making themselves useful. Certainly at the creative end, certainly at the level of educating people, the pedagogy of bringing up your children. So I think there's lots of domains which is not so obvious for me where robots can completely take over. I see more of it like the robots helping you achieve some things much more efficiently, much more quickly, much more accurately. So at least for now, I'm not worried that the robots are going to put everybody out of work. We may be just leading much more leisurely lives, doing less, cumbersome things. Maybe we have to go to the gym more often because you're always sitting on your chairs.
This is really, I mean, will we go through an inevitable stage of backlash and negative adjustment with robotics, or do you think by virtue of the way that it's developed we can avoid that? And if we are going to hit a crunch point where there's societal problems with the way that robotics is developing, what point in the future do you think that will be, in terms of decades, or is it 100 years away? Or can we avoid it?
Yeah, that's a hard one. So, so I think, yeah, I mean, okay. I think it is our duty to make sure that everything is as transparent as possible, so that people can make their own judgments in the use of technology in their lives, in their lives of their near and dear ones, and in society. There are some things which are very hard to predict the future consequences of. You know, take the GM story. So genetically modified food, the jury is up there in terms of whether, you know, it's the right thing to do or not. Do you enhance the amount of food that's available to people to prevent people from starving to death, or do we worry about some of the consequences of the genetically modified food affecting our future generations, maybe even now, in a way that is very subtle, very hard to predict? So I think it would be foolhardy of me to sit here and make predictions saying, you know, it's going to happen 20 years in time, blah, blah, blah. But I think it's a moral and ethical sort of duty about us to think about debate. I mean, this whole lecture is actually nice in that sense, that you can bring up very honestly some of the problems that may arise as part of the technology, and we should all go away, think about the implications, and think about what is, you know, whether you know, put open questions, so that when, I think the important thing is when there is lawmakers or sort of whoever deploys the technology, when they have to make a decision about this, they get an informed, balanced view of the things. And I think that's our duty, to kind of try and have this debate and inform us. But it's very hard to predict, I think. I'm not going to make a prediction.
When you say robots would help augment people's abilities to do things, to do good things, that also implies to it would augment people's abilities to do bad things, eventually landing up into hands of killers or terrorists, or having more fully autonomous robots who could just be programmed to be a more effective killing machine. Wouldn't it be just leading down a wrong path right now by setting that we should have a fully autonomous robot who we could program to do pretty much anything that we want?
So I think my stock answer to that kind of question is that that is pretty much true of any technology. We can use it for good and bad. That should not prevent us from improving technology. I mean, the fact that you can now, you know, communicate over internet over millions of miles with very low latency is helping you do many things, like educating yourself, taking a course from wherever, you know, across the world, making things accessible. At the same time, it's giving you the capability to fire a firearm, sitting this whole the drone debate. So I think that is, from a technological point of view, making advances which can potentially be used in either way is something that the society has to learn to live with and make sort of informed decisions. That should not prevent us from you know, making advances in technology. Okay, creating technology that is fundamentally and primarily and solely for what people generally agree is evil is probably not the right thing to do. But using technology, developing technology which can be potentially, you know, used, that is really a debate that the society should have in terms of who are the lawmakers, whom do we have, who has the actual final say about its usage.
Yeah. Thank you. I really enjoy your presentation.
Thank you.
I just want to bring the first goal that you mentioned about the robot that can plans,
Yeah.
then robot that can make its own decision. And then at the end, you're talking about the ethics issue. And I really grateful you brought the issue of the GM food, and also, for instance, on the Green Revolution regarding now we have more patent seed, which is not owned by the peasant, but by Monsanto, for instance. So I couldn't.
Sorry, I didn't get the last bit. Can you repeat
I'm
the
just
last
giving another example about how the Green Revolution, which is bringing a lot of food to us,
Yes.
but also at the same time making seed become privatized and farmers doesn't have access to a lot of seed.
Okay.
That's become, people see it as a access, as a,
Okay.
but however, there's a lot of in our history, this thing happening. And that's where I thought robotics it's very, very good, but also how do you reconcile the two of these robot that can make plans and make decisions. At the same time, to me, I see it as human giving up their decision-making in a way, and how actually that's become overlap. And that's where I thought the ethics issue should be discussed earlier, not when things went wrong, when it goes wrong. Because that's kind of doing the same mistake again and again. Like the drone issue, for instance, it's a robot, no?
Yeah.
That's what I mean. There's a lot of things in the history showing example how actually technology went wrong, but the ethics only become, especially with the perspective of utilitarian, when we don't put history, we don't put also this, a human is a creative. That's why it's not robots,
Yeah, so
and to
I'm not
expect
sure I
robot can solve every kind of this decision making and plans, and to me it's like, I don't want to give it up, personally speaking.
Yeah, I agree. I think there are certain things that you don't want to give up the decision-making abilities. Absolutely. So I think so my take on that is that yes, you should only allow or deploy robots in domains where you're comfortable with, and that's why we are having this debate, because I think there's a trade-off, and that is the classical thing, the trade-off between the benefits versus the volition. And when you sit in your car, I'm not sure if you drive, whether you're a bike person or a car person. You sit in your car and you switch on the ignition and you put the accelerator, and then further down you kind of press the pedal, press the brake. You are trusting at some point the machine to brake and stop the car for you. So already in many walks of your life, you are devolving. You're not literally physically, putting something to make it stop. You are trusting the electronics and the intelligence behind it will, and in many cases now the brakes are not even mechanically connected to your drive system. So in a way, you are already knowingly or unknowingly trusting some of the technology in everyday lives. Now the question is, where is the limit for that? You're absolutely right. We should have a debate about this. It is not. It is something that will evolve, and I don't have the answers to where and when we should, make sure where that boundary is. It's a hard one.
I'm really excited for when 2030 or 2045, when I can, when I'll have a daughter or a son, and I can pick them up from school in an autonomous car, and rather than focus on driving, I can sit and look them in the eye and talk to them about their day at school. Instead of having to watch the road, because the car will be doing that for me. The road's not interesting. It's not my daughter or my son. It hasn't had a day. It's just transporting me to my next destination, or us. So that's I just want to share that.
First of all, yeah, I'm excited about your talk. It's very interesting to see, but I'd like to pick up on the issue that the gentleman mentioned earlier about the killing machine and the misuse of the technology. And I was wondering, from a researcher's perspective, how do you, from a personal perspective, how do you deal with developing technology that could potentially be misused? And secondly, how do you manage to stay free in your funding? And you mentioned DARPA as putting up the DARPA challenges. Are there possibilities for you to do your research without relying on funding that comes from such companies or government organizations?
Right, yeah, thank you for that question. So I think so I do ask ethical questions of my research all the time. And as I said earlier in response to one of the questions, I'm very conscious of not developing technology that can be solely used in a sort of negative fashion. So having said that, if you look at technology in security, in sort of internet research, in compilers, pretty much all of these things eventually can end up in good or bad hands. So the only thing, so I make sure that the core. So when we develop, say, take a concrete case, we develop an algorithm or we develop a particular capability, we have an application in mind. So indeed, that application has to be, to a large extent, ethically verified and I would say vetted in the society. Of course, you can take the core thing that comes out of it and people could deploy it in any number of ways. And it's very hard for you to control and sort of, build a bridge, build a fence around what can be used, what can be done with your technology, with your, and that is more a job for the legislators to make sure that doesn't happen. And on the question of funding, indeed, that's the same, so similar pattern. So I make sure that a lot of the funding that we get is sourced in a sort of ethically sort of worthy cause. DARPA is an interesting case because the whole way the DRC challenge was set up was for health and rescue, sort of search and rescue in the sort of Fukushima disaster scenario. Again, it's a fine line to walk between getting appropriate support to make sure that the technology and the research progresses while making sure that the underlying philosophy of the person who's supporting you is correct. And we try to do that at every phase as much as we can.
So in your experience, at what point in the development of a project does the idea of this maximizing utility function actually come into play? And in your experience, has that been left to developers, or do they then bring in a bunch of people who want to decide that on a certain function?
So I think the honest answer to that question is that, except for a few examples like the prosthetic hand that you've seen and some of the other things, a lot of the technology that we developed are at such low TRL levels that so what it means is that it isn't developed to a stage where it is applicable immediately in the society. So a lot of the core research that we do are at the level of prototypes, are at the level of proof of concept devices that we, again, there's a bigger aim which is clear, but the question of how that technology, if it works, is going to affect the way we live and play is very limited in my research agenda. It's very, very different in some other places where people work on materials, in the GM foods, the stem cells, it's much more closer. But in my personal research agenda, the TRL levels are relatively low, which means that it doesn't mean that we don't think about the ethics. The goals are worthy, but we don't yet have to worry too much about how is that going to change the way people use it. And essentially, the usability groups, the people who actually take the technology and try to make it into product, they do that. There have been some of our spin-offs from companies, from some of our PhD students who actually do that. They look at both the societal impacts, the educational market, how people take this particular technology and what are the possible options. But in my personal research, the TRL levels are so low that we've not looked too much into that, except for a few products here.